This is a lesson on the uncertainty principle in a unit on modern physics. At this point, you should be getting an idea that particles are not particles in the way that we think about particles. Particles are these fuzzy things that most of the time on the planet Earth, we can get them to act like something solid and obey classical physics. But when we get them moving quickly, they are all of a sudden a fuzzy thing with no real location in space. And so it may seem intuitive while we're talking about this that there's some sort of uncertainty in its location, some sort of uncertainty in other things that we'd like to measure about this thing that we think is a particle that has wave properties. So with those ideas established, particles of matter have wave characteristics, and therefore there's an uncertainty of location in that particle. We saw that with the double slit experiment shooting electrons at a screen. There's some sort of probability where a single electron will land. We can't know for certain until it gets there, and there's a probability all across that screen. And we can think of the probability in terms of the intensity. There's high probability in areas of high intensity and low probability in areas of low intensity. The probability distribution in space, there's no definite location, and there must be some sort of limited precision with which certain physical quantities can be known simultaneously, okay? The math isn't actually that hard on this. If you take the wavelength and multiply by the momentum, well, the momentum we know is h over lambda, so there's some sort of just easy relationship relating Planck's constant in here. And it actually comes out with an inequality related to Planck's constant. There's some uncertainty in the momentum and some uncertainty in the position, and that has to be greater than h over 4 pi. And so we're seeing that the position and momentum cannot both be known at once. These can be rearranged. Momentum is related to energy, right? And we have a velocity in here and time. And so we can get time out of here. Energy and time cannot be known both at the same time either. So we get these relationships. And this is what we call the Heisenberg uncertainty principle because of Heisenberg, the quantum physicist. And this is a fundamentally important quantum mechanical property at a very small scales. When we think about particles, and maybe if we think about the fuzzy model of the atom now, where we have an electron acting like a wave through space, this is more how we can think about it. If there is a wide measurement, we don't know where it is in space. If there's a large variability in position, then there's going to be a smaller variability in momentum. We'll be able to measure the velocity of that particle easily. Whereas if we really locate it down to one spot, it could be moving at a lot of different speeds. There's a lot of probability of that. We really can't nail these down, and that has to do with the wave property. So these are pretty easy to apply in problems. Most problems are not very difficult in here, just looking at values. I picked a proton accelerator. The velocity of a proton in an accelerator is known to an accuracy of 0.25% of the speed of light. What is the smallest possible uncertainty in its position? So we have an uncertainty in the velocity, and we want the uncertainty in the position. So when I look at the equation, this is the uncertainty in the position here, the delta y. I can relate the uncertainty of the velocity to the uncertainty of the momentum. Classical momentum says P equals mv. So if I want to find the variability, the uncertainty in the momentum, then I would take m times the uncertainty in the velocity. And I know the uncertainty of the velocity. They tell me it's 0.25%, so I'm going to go 0.25% divided by 100. So it's like 0.0025 of the speed of light. So we're very much below that limit that I said that this will be accurate. V has to be less than like 10% of the speed of light, and we're definitely there. We're within the classical limit. So I'm going to plug what I know up here. I'm going to solve for delta y. It has to be greater than or equal to h over 4 pi divided by that variability, that uncertainty in momentum. And so here's the expression for the uncertainty in the momentum. m times 0.25 over 100 times the speed of light, c. And I can plug in the numbers here just to remind you, 6.626 times 10 to the negative 34th joules times seconds, divided by 4 pi, and then I'm going to divide by the mass of a proton, 1.673 times 10 to the negative 27th. Then I still have that 0.25 over 100, and then multiply by the speed of light, 299,792,458. And when you multiply all this through, when you run it through your calculator, 4.21 times 10 to the negative 14th meters. So that's the uncertainty in its position. When I look at this equation, and hopefully you've been coming along with your physics sort of analysis, thinking about evaluating this number. Does it make sense? What scale is it? What does that mean? Does it have any good implications? 10 to the negative 14th, we're definitely smaller than an atom. Definitely smaller than an atom, the nuclear part of an atom. But we're looking at a proton. We don't really ascribe a proton a size, right? Proton doesn't have a radius like a basketball or a baseball would, right? We're trying to locate this point particle in space, and we're saying 10 to the negative 14th in accuracy, which is actually pretty good. But if we're trying to locate this proton in an accelerator, we would have to have really, really good, accurate measuring devices in order to really nail down where this proton is. And even if that's true, there's going to be this uncertainty in it.